Consider a smartphone left outdoors in chilly weather. The device possesses an initial internal thermal energy storage capacity of 50,000 joules at 20 degrees Celsius above the ambient winter air. The phone's lithium-ion battery contains 180,000 joules of usable electrical energy when fully charged. The user initiates a 60-second high-definition video recording. During this period, the camera module and display consume a constant 15 watts of electrical power. Simultaneously, the battery's internal resistance generates joule heating equivalent to 2% of the remaining battery energy per second converted into thermal energy within the phone's chassis. This waste heat warms the device. Newton's law of cooling governs heat exchange with the environment, where the rate of thermal energy loss is proportional to the temperature difference between the phone and the ambient air, with a thermal conductance of 2.5 watts per degree Celsius. The phone's total heat capacity is 1,200 joules per degree Celsius. The video recording ceases precisely when the battery energy depletes to 1% of its full charge. At that exact moment, the internal temperature of the phone reads exactly 0 degrees Celsius. The question demands calculation of the ambient air temperature in degrees Celsius to 2 decimal places. This scenario presents a coupled system of ordinary differential equations. Let capital E of t represent the battery energy in joules at time t in seconds. Let capital T of t represent the phone temperature in degrees Celsius above ambient capital T subscripta. The initial conditions are E of 0 equals 180,000 joules and T of 0 equals 20 degrees Celsius. The battery energy differential equation is dd equals negative 15 watts minus 0.02 times E of t. The temperature differential equation is 1,200 times dt equals 15 watts plus 0.02 times E of t minus 2.5 times T of t. Notice the symmetry in the source terms for the electrical drain and the thermal gain. Solve the first linear differential equation for E of t. ddt plus 0.02e equals negative 15. The integrating factor is e to the 0.02t. Multiplying through yields dt of e times e to the 0.02t equals negative 15 e to the 0.02t. Integrating from 0 to t gives e of t times e to the 0.02t minus 180,000 equals negative 15 over 0.02 times the quantity e to the 0.02t minus 1. Therefore, e of t equals 180,000 e to the negative 0.02t minus 750 times the quantity 1 minus e to the negative 0.02t. Simplify to e of t equals 180,750 e to the negative 0.02t minus 750. Verify at t equals 0 to e equals 180,750 minus 750 equals 180,000. Correct. Now evaluate at t equals 60 seconds to find the termination condition. E of 60 equals 1% of initial energy, which is 1,800 joules. Set 1,800 equal to 180,750 e to the negative 1.2 minus 750. Add 750 to both sides to obtain 2,550 equals 180,750 e to the negative 1.2. This equation is a consistency check for the model's parameters. Solving for e to the negative 1.2 gives 2,550 divided by 180,750, which equals 0.014107. Taking natural log gives negative 1.2 equals natural log of 0.014107, which is approximately negative 4.261. This reveals an inconsistency because negative 1.2 is not equal to negative 4.261. The given parameters for battery drain and usage time conflict with the required final energy state. Therefore, we must adjust the constant electrical load to satisfy the boundary condition. Let the constant power draw be capital P in watts. The battery equation becomes d dt equals negative P minus 0.02e. The solution is E of t equals the quantity 180,000 plus 50p times e to the negative 0.02t minus 50p. The condition E of 60 equals 1,800 yields 1,800 equals the quantity 180,000 plus 50p times e to the negative 1.2 minus 50p. The value e to the negative 1.2 is approximately 0.301194. Thus, 1,800 equals 0.301194 times 180,000 plus 50p minus 50p. Expand the right side 54,214.92 plus 15.0597p minus 50p equals 54,214.92 minus 34.9403p. Subtract 54,214.92 from 1,800 to isolate the p term. 1,800 minus 54,214.92 equals negative 52,414.92. This equals negative 34.9403p. Dividing yields p equals 52,414.92. Divided by 34.9403. The result is p approximately equal to 1,500.0 watts. This is an unreasonably high constant draw for a phone camera, suggesting the model's time constant or percentage loss needs recalibration for a realistic device. To preserve the pedagogical integrity of the problem, we accept the mathematical parameters and proceed to find ambient temperature capital T subscript A. With E of t known, we solve the temperature differential equation. dt plus 2.5 over 1,200t equals 15 plus 0.02 E of t all over 1,200. The time constant for temperature is 1,200 divided by 2.5, which is 480 seconds. The right-hand side forcing function includes the exponential decay from the battery heating term. Let us define the particular solution and homogeneous solution. The integrating factor for the thermal equation is e to the t over 400.